Okay, this is the digital image processing, lecture number 9, a series of the lecture given for the digital image processing. And today I would like to talk about the perspective transformation. Perspective transformation is also called the image transformation, projecting the 3D project onto the plane. A perspective transformation play a central role in image processing because they provide a approximate to the manner in which an image mm, is formed by viewing a 3D world. This This transformation are fundamentally uh, different from the previous one that in lecture 8 I talk about. I think this one, this kind of rotation, translation, this kind of thing is fundamentally different from the uh, uh, previous one because they are non-linear in that they involve division and by coordinate value. So it's because it's involved the division, so it is nonlinear. Figure 2.17, this figure shows a model of this transformation process. The camera coordinate system is XYZ. Image plane coincident with the XY plane. So this is the image plane XY, but camera is the same, but in different cases also later I will discuss. And optical axis is important, optical axis along the Z axis. Thus the central of the image plane is at the origin and the center of the lens is at coordinate 0, 0 lambda. So length of this is camera and this is camera. Okay, and length of the camera is here. Coordinate is 0, 0, and z is the uh, light axis. It's lambda. So length is here, and object is here, and the image is here. This is uh, image surface or the surface that image projected here. The image plane. If camera is in front of the distance, then lambda is the focal length of the distance. Here, the assumption is that the camera coordinate system align with the world coordinate XYZ. So it is aligned. Later, I will discuss about different cases. And XYZ, a large XYZ, be the world coordinates because this is an object in the world, so at any point in 3D sense. So the perspective transformation project this 3D object point into the image plane, which is two-dimensional. This XYZ projected to XY only. This is very important. This is perspective. So I'd like to talk about this. This accomplishes a similar triangle. So the first step is to obtain the relation given the XY and XYZ. And this is by the similar triangle. There are two triangles, similar triangle. This is one here, project X, and this is Y. So this triangle and this triangle here. We can write this similar triangle formula here. So x to lambda is minus is inverted. X to z minus lambda, which is x to lambda minus z. And also y to lambda is minus y to z minus lambda, which is y over lambda minus z. This is very easily we can obtain from this figure here. I can show you maybe here is better also. Yeah, here is also possible that you can see that the XY coordinate camera and x to lambda is this x to z minus lambda, which why it is in because it's inverted, we put minus here, then it is minus lambda. Okay. So these two equation is important here. These equations are nonlinear because they involve the division by the variable z. Although we could use them directly as shown, it is often convenient to express them in linear matrix formula, like in this figure, sections 2.51. 2.51 for rotation, translation, and scaling. Before I told you this scaling, rotation, translation, and this is easily accomplished by using the homogeneous coordinate. So in order to make this expression such as the transform, translation, rotation, we use the homogeneous coordinate. What is homogeneous coordinate? The homogeneous coordinate of the point of the Cartesian coordinate x, y, z are defined by kx, ky, kz, and k. Usually in Cartesian is x, y, z, three dimension, but here the in homogeneous coordinate we have kx, ky, kz, and k. It is four dimension. So I mean that we have the last the dimension here is k, which is multiply of kx, ky, kz. So if each one divided by the last one coordinates, then you will return to the x, y, z, the Cartesian coordinate. K is just arbitrary, nonlinear constant, and conversion is very easy. Conversion to Cartesian is just accomplished by dividing the first three coordinate by the force, as I said. A point in well, let's see, a point in the Cartesian express is like this W here. This is the point in Cartesian coordinate. In homogeneous coordinates, its counterpart is this one. So W is here XYZ, and here WH is homogeneous coordinate counterpart or coordinate, which is KX, KY, KZ, and K. Okay. Now, if we define the perspective transformation matrix as this, so multiplying P, this is 1, 0, 0, 0, 0, 1, this, and so this is 4 by 4 matrix perspective transformation we define like this, and in the last section is 0, 0, and only 1 over lambda minus 1 over lambda and 1. This is due to the projection of the focal distance lambda. And if we multiply this perspective transformation multiplied by the homogeneous coordinate, we will get um, the CH, which is the image homogeneous coordinates, which is multiplying this by this you obtain kx, ky, kz, and the last one is this. Okay, as we defined the cx, if we want to find the ch, a camera coordinate in the homogeneous form, this as this as indicated, this coordinate can be converted to Cartesian coordinate by dividing the first three component of ch to the fourth. So Cartesian coordinate of this is, okay, Cartesian coordinate is c, which is x, y, and z. It become we multiply, we divide x, this one by this one by last one, and this one by last one. If we do this, you will see that the you have lambda x minus lambda and this. So it is very similar to the what I told you about the coordinates. So later I will discuss this, that this is the same. These first two components, C, are the same xy coordinate plane in 3D as shown in figure. The third component is no, we don't have any interest in the third one because it's only two-dimensional. Then this component, as shown, this component acts as a free variable in perspective transformation. Okay. So in order to, okay. Hmm. So let's stop here maybe, and then I will continue from here. For inverse, okay. For inverse transformation, the inverse perspective transformation, I mean, inverse transformation map by 3D into the 2D. So we put P inverse CHWH. So we make this P inverse, which is this one. If you compare with the previous one, only minus is removed from here. And suppose that the coordinate x0, y0, z0 for the image point, and 0 is the location of the z, of course, because z is 0. The homogeneous coordinate is obtained like this, and then it becomes c. ch becomes kx0, ky0, and k. If you multiply this by this, I mean this one, let I show you again. This coordinate ch is here, this one, multiplied by this one, then you get this one. And then you will get this one, which in the Cartesian coordinate, you can divide is x0, y0, and z, which is the x, which is x, y, z is 0. Of course, this is then inverse is impossible. This is a little bit strange because this result obviously is unexpected because it gives z equals 0 for any 3D point. So because we cannot return from 3D back to from 2D back to 3D, we can project 3D to 2D, but 2D to 3D is impossible because you are back perspective transformation is impossible, and we get the z equals 0. The problem here is because that by mapping a 3D set onto the image plane, which is many to one transformation. This is many point can be transformed to one point. So this is impossible to return to the space, to the uh, point, real space. The image point is x0, y0 corresponding to this 3D is x0, y0. Let me go there on the next page. And so here we can say that, let's see. And here is page 59, 56 is here. Okay, sorry. Okay, yeah. And 0, lambda, the equation, this line in the world coordinate system becomes like this, and then x is equal this from this equation. This equation, I think I can show you 1819. 1819 was here. Yes, this two equation is for perspective transformation, so it's exactly the same here. So from these two equations exactly the same. So x is this, y is this. So this equation 30 and 31 show that only something is shown about the 3D that generate an image point. For example, z coordinate is it is not possible to complete recovery 3D. This observation, which certainly is not unexpected, can be used to formulate the inverse transformation. So by using z component as free variable, so we can do this. CH is K0, KY0, and KZ. So we assume a free variable, free component using a Z component CH as a free variable. If we put CH here, we put CH. If I can show here, CH, I think it's, okay. Let me show here. Yeah, CH was with 0, but here we don't put 0. We say just a free variable Z, KZ, and K. This is homogeneous, and it follows from the equation 25, and that then the if we multiply the inverse perspective transformation is this one, which open the conversation Cartesian, we divide each one by the last one. So x, y, z is this. We don't need this one, but anyway, it is here, okay? But anyway, this is important. So I will, now I will explain more here. It's very important here. And then we have three equation here with using a z, small z as a free variable. Then x large s is this, large y is this, and large z is this. This small z is free variable, but this is important in a sense because we can find z from here, solve z in terms of the upper z in the last equation and substitute into the two expressions. Then we obtain these two equations. These two equations is very important because what we get from the, I told you about in the perspective transformation here, what I told you here is exactly this one. Is exactly these two equation is same as these two, but just here we find the large x from the small x. We calculate large x and upper y coordinate of the uh, board coordinate from the image coordinate. If you obtain from this equation, is exactly the same, this equation. If you obtain x and y from the image coordinate, is exactly will be this one, which it means that which actually the observation of the 3D. So it means that in order to find the back perspective, which is 2 to 3 dimensional project projection, is impossible unless otherwise we use the free variable z, and then any point in the image coordinate can be mapped to the world if you know the uh, this kind of the information. I will tell you more. By, by means of this inverse perspective proposition requires knowledge of at least one world coordinate. So we need 1 point coordinate here. For instance, z here. If you know z, then you can find the coordinate at the space of the in the world. If you know the coordinate of the z. This will address later this problem in this section in order to find the distance by using two camera. And here, after I define about camera model, and also I will discuss about the stereoscope in next lecture. I think this one I can finish here if I have enough let me see again. I will tell you here from the slide here again, this perspective relation, and here is the uh, perspective relation here, and then the Cartesian coordinate and homogeneous coordinate is important, and the conversion is this one is just by dividing the first three component to the fourth component, and the perspective transformation is like this, and this is lambda is the focal distance of the camera, and multiplying the homogeneous coordinate, and we define homogeneous coordinate like this, multiplied by the perspective transformation, we get the homogeneous coordinate at the after transformation. And then later for inverse, and then we find the Cartesian coordinates by dividing the first three to the last, like this. And by inverse, in the inverse perspective transformation is like this. If we multiply by this, then we return to the word again, but here if the zero is very unexpected result, so we use the free variable z here. After using z, then multiplying by p inverse, we get the word coordinate in homogeneous, and then dividing by the last one, each coordinate by last coordinate is the word coordinate in Cartesian coordinate. And from the last one is the free variable z. From we calculate small z from the upper z, and then uppercase z, and then put to here, and then find the equation like this. X is this, y is this, which is same as the perspective coordinates. And that is same as the show the inverse transformation result is at least one component of the world coordinate of the point. Requires the inverse transformation at least requires at least one point of the coordinate. If you have the one point, then you will get the world coordinate. This will be discussed in later in camera model. And here I stop, and then perspective. And thank you very much.